So next up is the social media guy for React.js. What's a nice title? So welcome to Pete Hunt.
Hey, I write code too, Chris. How's it going? Yo, like the announcements here were pretty killer, I thought. Didn't you guys? Like native apps in React, like, I don't know, if anybody was worried about their careers writing JavaScript on mobile, like, don't worry about it. But I actually am really excited about Relay. That's my favorite thing because just fetching data is such a pain and it makes such a difference. Anyway, I'm going to talk about the future of JavaScript layout systems. Basically, at the end of the day, it's probably not grid style sheets, which is the thing that I was going to talk about. Sorry. So I built V1 of a product with grid style sheets, and it's a very interesting abstraction. So it boils down, there's kind of this one atomic abstraction that you get, which is a constraint. And you can say, hey, I want this box's right-hand side equal to the left-hand side of this other box, and it will line them up for you. Now, the problem with that, even though that's really elegant, the problem that I found is that the solver is unpredictable. So the cassowary constraint solving algorithm is non-deterministic. What that basically means for kind of an app developer is that when you change the dimensions of a viewport, you make the viewport really big, and then you make it small again, your layout breaks. And it's very difficult to debug that and understand where the constraint was missing. And at the end of the day, I just started writing CSS. And it was sad, but we make it work. Anyway, so today I'm going to talk about full stack Flux instead. Cool. All right, so what does this even mean? It's like two really trendy buzzwords, I feel like. But what I'm talking about is the architecture of the backend systems that I've been building at my new company and how they're related to Flux and how Flux has actually saved us from a lot of headache. So I'm going to talk about a couple of things. I'm going to review Flux kind of from my perspective, the problems that I think it solves. I'm going to talk about the current state of the backend. So I was working a lot in front end, and I kind of recently entered the backend world, and so I have a little bit of a unique perspective on that, I think. And then finally, how Flux can save us. So let's talk about, let's kind of review Flux. And the example that is always used is Facebook chat, and I think it's a pretty good example. And so messaging is a very, very competitive space because there's so many different companies competing. They're building these features all the time. But if you drop even a single message, that's hugely bad. So you have to be able to ship features and also maintain a certain level of reliability. And so let's talk about how we would build a feature on Facebook chat using the old non-Flux way. So at the bottom of your screen on www.facebook.com, you'll see a selection of threads, and they have an unread count on unread count of messages in red. And so if we were building this in a traditional way without Flux or an MVC framework, we would build it something like this. We'd receive an event from the server called onNewMessage, and it has a message object. We would increment the count of the unread messages in that thread. So we have a data structure somewhere that holds onto that count, and then we update the DOM. Follow so far? I'm not seeing anybody throw up, so I'm not sure if you guys are following along. Anyway, let's say that we want to build another feature that we didn't think of before, which is highlighting the number of unread threads in your application. This is a feature that they didn't think about when they were shipping V1, and now in V2 they want to ship it. Again, agile development. We don't know what features we're shipping until we're already building them. What this boils down to is a new question that we're asking of our data. So we've got all of this data on in our browser and in our databases, and we've only ever asked it, how many unread messages do we have in a thread? We've never asked it, how many total threads are unread? So if we were going to build this in the traditional way, we'd take this old event handler that we built for our previous feature, and we would augment it with some additional code to handle this use case. So keeping track of the number of unread threads. If we're incrementing the number of unread messages from 0 to 1, then we increase the number of unread threads. It's more code to maintain. So that's what happens when we add a new question that we're asking of our data. How about when we add a new action or mutation of our data? So let's think about trying to send the state trying to send the message read action from a mobile device to your desktop browser. So when I open my phone and I read a message, I don't want it to show up as unread in my desktop browser. So we're going to have to add a new event handler called onReadFromMobile. And we're going to have to do pretty much the same stuff that we were doing before, keeping track of the data and mutating the DOM. But the key thing is we have to consider both questions that we're asking of the data. We have to keep track of the number of unread messages per thread and the total number of unread threads. So every question that we add, we have to go through every single action handler and update them to answer those questions. So you guys know this. Shared mutable state is the root of all evil, but emphasis on shared. So the fact that we do have mutable state in our application and we're mutating it from multiple places makes it even harder to understand than just regular mutable state, which is pretty hard to understand. So there is an alternative, and it's basically built around observation. So this is a much better approach because we don't have to sprinkle DOM manipulation throughout our code. So this is all made up libraries, but we have an observable data model here where we have unread message counts, the total unread thread count, and we add listeners on both of those data types, and we mutate the DOM when those change. So the DOM updates are all consolidated in one place. And then our event handlers for the events coming in from the server become much simpler. There's no DOM mutation in there, just sets and gets on these observable data structures. And so we don't have to repeat that DOM manipulation code between the onReadFromMobile event handler and the onNewMessage event handler. So that's pretty great. That's definitely an improvement. But there's still a problem. We still have to answer both questions in both action handlers. So we're still dealing with the unread message counts and the unread thread counts in our onNewMessage event and in our onReadFromMobile event as well. And if we want to add a new feature like marking a thread as unread, we're just going to repeat that code again, keeping track of the unread message counts and the unread thread counts. So again, we're adding new features, and we have to answer every single question we might answer, or we have to keep track of every single question we might ask of our data for each action we get. Again, shared mutable state is the root of all evil. And there's a race condition here too. If I click mark unread, but the server comes back with a reading from my mobile device saying I read the message, and those arrive in the wrong order, I could click mark as unread, and it still shows up as read. That's really bad. So what Flux does is Flux consolidates this into one module. What I mean by this is that just looking at this module, you know exactly how the state of unread counts is going to change. Every single action that can possibly change it is in one place, and nobody can directly mutate this. Same with the thread store as well. So all of the questions, so we only have to think about the questions we ask of threads in this store. So the way I think of Flux is it helps you scale actions and questions. So in each of those stores, we just list the actions we're interested in, and we only answer one question. And it's a very nice way to organize your code. But we should probably talk about infrastructure and the backend. We actually face similar problems to this when we're building backend services as well. If anybody's ever built a kind of highly trafficked website, you'll have this very common pattern where you'll want to get some piece of data out of the database with a query, and you want to cache it. Caches are much faster than databases and much less expensive. So first we try to get the photo from the cache. And it's got a cache key. The name of the cache key is photo, and it takes a photo ID. The photo's not in the cache. We go get it from the database, and then we add it to the cache, and then we return the photo. Does this make sense? Have you guys done this before? All right, cool. Great. So if we want to increment the number of likes on a photo, we would do something like this. We would do a write to the database, and then we would delete that cache key from the cache. It's called cache invalidation, and you may have heard of it before. It's one of the harder problems in computer science. So this is OK, but I think you guys can see where this is going. If I want to add a new query, or I want to ask a new question of my data, like what is my most liked photo, I'd implement an accessor like this, and I'd have to cache it separately from the other accessor. So first, I would try to get the most liked photo. If it's there, great, return it. If not, I get all of my photos, I take the one with the most likes, and then I save it back in the cache before returning it. This is the exact same pattern as the other method, just a new question we're asking of the data. So if we go back to my increment likes method, we're going to have to remember to not only expire the photo cache key, but also the most liked photo cache key. And we have to keep track of every single place that this photo object is going to be in the cache. And you can imagine that's going to get really, really ugly really quickly. It's just like manual DOM manipulation without something like Flux. So what would a server-side Flux implementation look like that would solve this problem for us? First, we should probably think about what a Flux store actually is and think about it in a little bit of a different way. The way I think about a Flux store is I think about it as a reduce plus a change event. What I mean by that is that a Flux store basically takes in a log of every action that ever occurred in your application, does some thinking about it in a mutation of its internal state, and then returns the current state and emits a change event if that state has changed from the last time you called it. We call this derived data, and it's derived data from the entire action history of everything that's happened in your application. There's lots of types of derived data in your application. Query results are derived data from the actual data in your database. Database indexes, you run create index on a SQL table, and it scans the whole table and creates a new index. You can recreate that from that table at any time because that's derived data. Caches, like I just mentioned. Search indexes, so if you want to run something like Elasticsearch or Lucene, you generally build that index out of data that's persisted in a durable store like MySQL or something like that. Data warehouses, they're generally not your primary data store, but you need to ask questions that you might not know that you have to ask when you index it. So these would be arbitrary queries from your data scientist. Database replicas, sharding, it's all derived data off of the history of every single action that's ever happened in your application at every level. So it's derived data from every single action that ever happened in your application. Now, if you think about it, understanding the use case for database indexes is easy, but I think it actually applies on the client as well. We take every single action that the client receives, and we aggregate it into a data structure in a Flux store, which then gets read by a React component, which then returns React elements that then get transformed into DOM operations that then get applied to the browser and turn into pixels. So we're deriving data at every single level here. We can compute the next result from the previous result and go all the way back and end up at a log of everything that's ever happened in my application. So all we have to do is send every single log entry in our app to every single client, and we can have a very reliable, easy-to-understand application. Does that sound like a good idea? Well, they laughed at JS Conf US when they said re-render on every data change. The real question is, can we make it fast enough? So I'm going to use a photo site as an example. So this is a very, very high-level idea of how we would set this up. We'd get an action. It would go into a message broker. The one that I have a lot of experience with is RabbitMQ. And then we would have our stores listening on that message queue. So a message queue, if you're not familiar with what it is, it's basically equivalent to a dispatcher, except since dispatchers run on a single machine in generally a transient session, they can be very, very simple. Whereas a message queue in a distributed system has to have a lot of really important properties. Like it has to be fast. It generally has to be durable. So when you save a message into the queue, it's saved and doesn't go away if the entire system crashes. It's shardable. So if you have multiple consumers listening onto a message queue, you can say, hey, send keys 1 to 500 to this server and 500 to 1,000 to this server to spread the load. It's compactable. So you can say, hey, this message that I'm putting into the queue completely supersedes other messages of this type. So feel free to delete the old messages. This is very, very important in making the system work. And finally, the message queue has to be cheap. Now, there are people spending their entire careers building message queues that have these properties. So I'm not going to go into how exactly they work, but they have built lots of these pieces of software, and they can manage these trade-offs for you. So if we want to basically answer these two questions about our photo sharing site, get data about this photo, and get my most liked photo, the way I would architect it in this system is I would have two stores listening on our message queue. And if we look inside one of these stores, it's basically a little bit of code and then some piece of mutable state. Your Flux stores are like this. But in a distributed system, this mutable state doesn't have to just exist as variables and data structures in memory. It could be a MySQL instance, for example, or a Redis instance. Or it could be persistent data structures existing in memory. So in this photo store action, we receive a like action. We execute a SQL statement to bring our local mutable state up to date, rather than appending to an in-memory array or something like that. And then when we ask this store a question, we say, hey, get the photo. It just runs a SQL statement to get that out of MySQL. And so there's lots and lots of advantages to building your system in this way. If this were warming a cache, the data would always be warm. And you can manage what data is in the working set and which data is out of the working set. Sharding becomes super easy. These message queues are already designed to shard their messages and point them at different stream consumers. So as long as you can answer, as long as your store is structured in a way that you can answer those questions in a sharded way, you just configure your message broker, and you can reshard very easily. One of my favorite properties is that rebuilds and migrations are a joke. So these stores, they are accumulating state. And if those crash, you lose that state. But with a message queue, you can just replay all of the messages that it had received in the past because it's durable, and you've pushed that complexity out to the message queue, and it will eventually bring it back up to a consistent state. Migrations are the same way. If you want to index your data in a different way, just write a new store, bring it up. Eventually, it will come up to date with the new data, and then you can cut over to it. And this actually plays very well with the trends in infrastructure these days. So if you've heard of systems like Docker, for example, they're designed around stateless services. And if you go and talk to the people that are using these and you're like, hey, how do I Dockerize MySQL? They look at you funny because it's a stateful service. And a lot of these pieces of infrastructure are assuming that your services are stateless. So if we can make as many of our services stateless as possible, they're a lot easier to maintain. So we push that state into the distributed message queue. But maybe the most important trade-off, or the most important advantage, is you can manage the trade-offs of your data store. So every question that you ask is going to require a different set of trade-offs. And we often don't know what questions we're going to ask at the beginning. I feel like this pretty well describes product development. So we need to choose the best data store for the questions we're asking in the data. And we also have to choose the best data store for the questions we're asking in the data at the current life cycle of the project. So when I start a project, and I'm sure that a lot of people have had this experience, you throw a bunch of data into some schema-less data store because it's easy and you don't have to think about it. And then you start seeing more and more weird bugs, and you eventually bite the bullet and make a versioned schema, and you start using SQL or something like that. So there's a lot of concerns. Schema versus schemaless is one concern. Write latency, how long does it take for writes to show up? Read latency, how quickly can you get a response from this? Query flexibility, do you know the questions you're going to ask of this data store ahead of time or not? This would be a SQL data warehouse versus a key value store is a good example. Costs, can you afford to spend a lot of money on this, or do you want to keep it really, really cheap? That's affected by the amount of data you're storing in it. Durability, is it okay if we lose this data? Or can we just rebuild it when we restart the service? So we get to manage that trade-off, and we can really kind of understand what our cost structure is going to be for each query that we're going to answer. So I think that this is a pretty attractive way to build systems today. So we started moving over a lot of our traditional infrastructure to this technique. But there's some more advantages too. Remember, this is how we've set up our system. We have an action coming in, goes into our dispatcher or message queue, whatever you want to call it, and then it gets passed to our store. So that's all we've talked about on the server side so far. But remember that stores can emit change events too. That's part of how Flux works. You receive actions, they emit change events when the data in them has changed. So rather than asking our stores on the server, hey, what is the value of this query, or what is the value of this photo, we actually subscribe to queries. And we say, hey, let me know when this photo is changed. Please tell me all the information you have about this query that I'm sending. And you start to get an architecture that looks a little bit like this, where we have actions coming in, updating our stores on the server, and then we have clients subscribing to changes to those stores, which drop those actions into the dispatcher on the client, going through the Flux stores on the client, activating, driving some application logic, sending actions back into the server, and then you've kind of closed the loop between the way that your data looks on the server and the way that your data works on the client. And you can manage trade-offs at each of these phases as well. You can decide get photo really, really needs to be fast and needs to live in Redis and in memory. Or you can decide you want to keep it very, very cheap and use it and store it in something like MySQL. You can also decide whether you want to request this data once, or you can subscribe on any interval that you want. You can just adjust these trade-offs at every single individual component. So this is great architecture, but there are some things that didn't work too well for us. The first was communication between stores. The way that it's specified in Flux doesn't work in a distributed system. Specifically, waitfor. So if you have two stores that depend on data, so a good example is the Facebook chat example, where in order to know how many unread threads you have, you need to know how many unread messages are in each thread. The way you set that up in Flux is the thread store waits for the message store to run and then reads from it. Now, in a distributed system, the thread store or the message store might go down, they might hang, they might be in some sort of intermediate state, or they might just take a really long time to process. And if you're blocking on all these different stores, then your system's just not going to make any progress. So the first option that we did was we just kind of bit the bullet and made a shared database between multiple stores. So this removed a lot of the advantages of our architecture. So if we have our photo sharing site and we want to blacklist certain images, and we want to make sure that images on that blacklist don't make our popular page, we're going to need to run a slow-running image classifier on the image. And when that's ready, we can finally make the decision whether we want to show this as a most liked photo or not. So if we wanted to communicate between these two, one option is for the isBlacklisted store to just share a database with the getMostLikedPhoto store, and that's how they talk. They basically, you put a bit in the database that says, is this blacklisted? And then when you ask getMostLikedPhoto what the most liked photo is, it checks that bit. This kind of sucks, and it throws away a lot of the benefits of this architecture, because this MySQL DB is now stateful, and you can't just throw it away. But at the same time, your architecture is probably already set up like this. So if you want to gradually migrate to an architecture like this, like we did, you can do it. But the better way to do it is to enrich your data. So in Flux, traditionally, a store consumes an action, does some thinking about it, and emits a change event. And Flux is very, very opinionated. It says you cannot emit an action as a result of another action, because that causes cascading updates. Now, unfortunately, we have to be able to do that in our distributed system. There's no way around it. But we can do it in a way that's controlled. And I'll give you an example of that. So if we wanted to do our isBlacklisted store, we would take in an image object, which has an ID and an image URL. We'd run our slow-running classifier on it, and then we would enrich that action and add a blacklisted field. And it would be of a new action type. Now, we can't just drop this back into the queue, because that's very, very dangerous. That causes a cycle, and getting the system into a cycle would just be a very, very expensive proposition. So instead, we want to set up our system as a directed acyclic graph, or DAG. Now, in Flux, traditionally, there's one dispatcher, and all of the stores are listening on that one dispatcher. In this system, you can plug the outputs of some stores into the inputs of other stores. And this is how most stream processing systems work in production today. Another thing that Flux kind of assumes that you can't really get with this system is strong consistency. Only the individual answers to questions will be consistent. Now, what I mean by that is that there's no coordination between the stores, really. You have no guarantee that my photo store is up to date with my most popular photo store, or most liked photo store. You can do some things like you can ask, hey, give me information about this photo that is valid after a certain timestamp, but it's still like fairly ad hoc to do that communication. But the good news is that this lack of strong consistency is actually kind of a more accurate view of the world. It's very, very difficult to build a scalable system that is truly consistent. Now, the canonical example people use of needing strong consistency is like a bank account, where you don't want to be able to withdraw more money than you already have in it. People have heard this example before? I've actually done that before, and you can do it. Yeah, I left Facebook. The way the world works is that there's latency, and so it's very, very difficult for you to construct a truly consistent system. So almost all problems can actually be modeled more correctly as a gradually, like eventually consistent system based on a log. So at the end of the day, I suggest you read more about stream processing frameworks on the server. They're really, really interesting. A lot of the work from the Apache Samza team has been great. I saw this talk at Strange Loop by Martin Kleppman. It's called Turning the Database Inside Out. It's very, very easy to understand, and it's just super cool. And most of the stuff that I talked about and that we've implemented at my company are repackaging of his ideas. Thank you. Cool. Do we do questions at this thing? I don't know. Oh, I can take questions then. Do people have questions? Hey.
Have you looked at the message queues that they're building specifically like Crossbar and Audubon, like JavaScript type message queues that can do some of this stuff?
I've looked at like the more traditional job queues, like it's called Q, K-U-E. Like we're kind of moving to more of like a streaming system. Like we're kind of abusing RabbitMQ for this right now. We'd be much better off with something like Kafka from Apache, but I haven't actually looked at those systems specifically. I will say that we started out with just abusing Redis for it, and it was pretty terrifying. It was fast, but it was terrifying.
Is this a solution you chose to solve scaling problems, or do you think this is a better way to architect systems, even if you're not having scaling problems?
That's a really good question. I view it very similar to how I view React. Like, you fall into the pit of successive performance, but it's a way easier model to think about things. So the big advantage for me is that we don't know what queries we're going to need on our data set right now. And so if we can just make the cost of migrations really, really low, then we can build all sorts of features a lot faster. So that's why we use this system, is because I can just spin up a new instance, like delete the old one, and then eventually it'll come up to date.
Cool. Hi.
Oh, hey.
So this is a problem I've seen a lot in web Flux, where we have questions and they aren't particularly answerable by a single store. So the idea of being able to query, say, the state of multiple stores comes into play. And I've run into this, and my solution has been to kind of decouple the asking of the question from the state of the store. Is that the pattern we're seeing here? And if so, why is there still the notion of stores being able to kind of answer their own questions if we're ending up composing these stores together?
So I think that it's not too often that you actually need stores to communicate with each other. Like, the reason that we're doing it is because of performance. So we absolutely, like, we do not want to rerun those classifiers multiple times. On the client, like with regular web Flux, I think that you just make the question more broad. And the way that I think about it anyway is I would, if I find myself, having a bunch of stores talking to each other, I would just kind of merge them into one store and like decouple the action handler method into separate functions. Because if you're starting to see stores coupled together, it's really like, are those separate questions, or are you really answering one broader question? And then because you can have stores all listening to the same events, you'll still get the data synchronization between them all.
Okay,
Does that answer your question?
Yes, it does. And my follow-up to that is, in the example you gave, does a store actually have reference to another store as a source of state when you're composing them together?
In the server-side example?
Yes.
It receives a message of type blacklisted image.
Okay. So it receives a message that's emitted by another store that doesn't go into the main queue.
Right. So you get to a point where you're manually wiring up the stores together. So there's a mapping of which stores are wired together, and then when you emit that new event, it's of a new event type as well.
Thank you.
Sure.
So since you can construct or reconstruct a table from the log of events, why have separate stores for each different query you want to answer instead of just having a table that can answer general queries like SQL?
That is a good question because you want to manage the trade-offs. So if we have one big table that can answer all the queries, it's called I guess people know Hive, right? Yeah, that's basically what Hive is. It's this big data warehouse that takes a day to aggregate everything, and then when you run your query, it takes 20 minutes to go. So that is like the right set of trade-offs for like a data analytics suite maybe, but not for when you fetch the profile page. And at that point, you do need to do some kind of mutative thing to make that index fast.
Right, but in like the client-side store is already listening to like kind of a subset of the data you care about. So you already have that limited, right?
Mm-hmm.
Like so you could have just like a table that has only the data that the application will ever query, not all of the data.
On the client?
Yeah.
Yeah, I imagine that's probably how Relay works.
Yeah, kind of.
Yeah.
Thanks.
Cool.
I have a quick question.
Sure.
You said that shared mutable data is the root of all evil, but previously you said that data changing over time is the root of all evil. I'm just curious when you changed your mind.
You know, the past 2 years have been a time of introspection and thinking. I'm just very happy that I was able to be a part of this community. I don't know how to do this like political stuff. Means the same thing, Tom. Yeah. Yay! All right, cool. Thank you.